Well, hello everyone, and welcome to the webinar on PCB design with differential data transmission. My name's Ben Jordan, and I'm hosting this webinar today on behalf of Altium. And hopefully you'll find it fascinating, interesting, and very useful for your own designs. The principles we're going to talk about today really apply to any kind of PCB design, whether you're using an Altium product or not. But of course, we will finish up at the end showing how to set these things up in Altium Designer. And as we go, I will be launching occasional polls to ask a few questions of attendees. I'd really appreciate your feedback in those polls. And at the end, we should have 10 or 15 minutes to open it up for a question and answer time. If you have any questions at all to do with the presentation or with Altium Designer, I'll do my best in a short time to provide answers for you. So with that, let's just jump right in. Okay, so this is our agenda for today. We're going to talk about what is differential data transmission and where does differential data transfer apply. We'll look at some of the parametric information that's important to differential design. Please excuse my printer going off in the background there. Someone's printing something nearby. In case you're wondering what the noise was, no big deal. Then we're going to talk about how we set this up in PCB design for differential pair. What are some of the things you need to consider when setting this up? We'll talk about differential impedance and design requirements for a differential pair. And then of course, finish up with the demo of the software, how we set this up and actually do it in design. So differential transmission is the transmission of two complementary signals over identical coordinated transmission lines in equal but opposite voltages. So, and currents that are applied to both conductors. So in other words, we send the same signal twice, but inverted. And we want to make sure on a PCB design that each of those signals is exactly the same length. And we route them together. Why? Because it increases immunity against external electromagnetic interference and crosstalk. It reduces the radiated interference and crosstalk from the pair itself. It allows for lower voltage operation, which we'll talk about in a moment. And as a result of that, and the added noise immunity, gives us the possibility of running much higher data rates. So differential signaling was developed first in the cabling before it found its way onto printed circuit boards. But the whole point of it is to be able to send more bits faster. So the main disadvantage, of course, is that we have more conductors for the same number of bits. If we want to send 8 bits differential, we need 16 transmission lines plus the return ground. So it can increase the amount of routing. On the flip side of that, though, usually because differential buses go so fast, they're typically serial buses. And as a result, we're using fewer signals. So it works both ways. So differential signaling began, as I mentioned, with cables over telecommunication transmission lines. And a true differential signaling system is what's called a balanced line, where we have galvanic transformer isolation between transmitter and receiver. And this allows a tightly coupled twisted pair of wires, such as you'd find on a plain old telephone system or in Ethernet. Ethernet cables have twisted pairs for transmit and receive, and 10 gigabit Ethernet has 4 pairs, 2 for transmit, 2 for receive, and these are true balanced differential lines, and they're twisted pairs so that the physical close coupling of each wire and its return path form a complete current loop between the transformers, and because they're physically close to each other, interference, common mode interference happens to both at the same time. And this means they are relatively immune to external noise sources outside the actual transmission line. And what this looks like in a digital circuit, and this marvelous picture comes from one of the Wikipedia contributors, so I just wanted to give some credit where credit's due there with the image source. But basically, we're looking at the transmission chip, we have a buffer that has an inverter and a true output. So we have a true and its complement, and that's inside the I/O of the actual chip. And the complement goes down when the true goes up, of course, and they're inverted. External noise is superimposed over the differential pair as common mode noise. So it happens, it's called common mode because it happens to both. And the receive chip at the other end of the transmission line, either over cable or across a printed circuit board, is a differential comparator. And the differential comparator only pays attention to the signal of the true and the complement when they are equal and opposite. And that allows it to filter out the noise source from an external radiated source. There's one thing to be careful of and bear in mind with this kind of setup on a printed circuit board and PCB, like chips on a PCB. That differential comparator at the input of the receive end is actually going to a MOSFET diff amp. So I'm just looking at one of the two pins in this example, just as an illustration. Typically what's inside the chip, which is that rectangular yellow area there, is it goes to the gate of a MOSFET, and so it's a capacitive load. It's a capacitive load, and to protect the silicon device, they almost always, it's pretty much invariable that they have Schottky barrier diodes or some sort of TVS diode built into the silicon that will isolate inputs, or not isolate them, sorry, wrong word. It will short inputs to VCC for input voltages that exceed VCC plus that forward voltage drop of that Schottky diode, which is usually about 0.5 volts. And similarly, if you have a negative going pulse, if there's added noise or an excessive voltage ringing on that negative going pulse, the clamp diode to ground will short from the ground of the chip minus 0.5 volts or thereabouts, the forward voltage drop of the Schottky diode. And so what can happen is if you have excessive common mode noise, it can still lead to error in reading the bits in a differential input, just because of that clamping, that diode clamping that can happen. So just be aware of that. It helps, but it's not the panacea that we think of it. And you can usually tell some manufacturer data sheets include a table. Some may even include a circuit diagram that gives you the equivalent input circuit of their device, and they'll show you the clamping diodes. Others will simply give you a table like the absolute maximum ratings, and this is what gives it away. In this example here is the data sheet for a low voltage CMOS device, and we can see that the input voltage range can go from negative 0.5 volts, seems like the forward voltage drop of a clamp diode, up to 6.5 volts maximum. And the output voltage range applied to any output in a high or low state can be VCC minus, can be from anywhere from minus 0.5 volts, again, that's that ground clamp diode there, to VCC plus 0.5 volts, that's the VCC clamp diode. So you know those clamp diodes exist even if they don't tell you about them in the data sheet. So just be aware of that. So where do differential data transfer systems apply? They apply when you're routing high-speed signals between devices that use differential signaling or from board to board. And the example I'll be showing you today is part of a multi-board assembly where we have some mini PCIe, and PCIe is a differential signaling standard. It also happens to use the USB 2.0 connection, which is a single differential pair that will go up to 480 megabits per second. And so we have various different standards from chip to chip or board to board, like LVDS, low voltage differential signaling, which is one of the most well-known ones. It's been around for a long time. Low voltage positive emitter coupled logic is typically signaled across boards, not always, but typically a differential pair. Serial ATA, which is used for mass storage devices on motherboards and such, PCIe, XAUI, there's numerous ones. And off-board, we have other differential signaling systems that some of them are more oriented towards cabling, like RS485, 422, or IEEE 802.3, which is the Ethernet standard. But of course, we have others like USB, HDMI, DVI-D, and these can exist on a board or go off the board to a cable, and you're all pretty familiar with those. So one other thing, just with this diagram here, the circuit diagram at the bottom showing the receiver, I mentioned in the last slide that typically our inputs are MOSFET gates. And so those are capacitive loads that have no DC path, and they're usually pretty high impedance. To get proper signal integrity and to not have excessive ringing or reflections on our diff pair, then differential signaling standards are invariably defined to have a differential termination or load that's resistive, and typically that's a parallel termination from one signal, from the true signal to the complement at the end of the line close to the device, but not necessarily, but usually that's where you place the termination resistor, towards the receiver end of the line. And again, it depends on what signaling standard you're using. If you are doing something else like LVPECL, then the input devices of the receiver chip may have enough of a load to be self-terminated. And of course, there's other newer technologies now, like we have with DDR memory chips. As of DDR2 and later, there's a feature called on-device or on-die termination, or ODT, and this provides the termination of some of the signaling, some of the high-speed lines actually in the die of the chip, and you can enable or disable that when you configure the device on power up. Also, the transmitter looks like an H-bridge, where we can send and receive current in the loop, but it's all coming from VCC and syncing to ground. So whether you like it or not, a differential signal on a PCB is always it's not just two signals. It's not a true and a complement. It's three: true, complement, and their reference ground on a PCB. It's not like the old analog microphone for a PA system where you have a long balance line cable and you may disconnect the ground in some situations, or disconnect it at least at one end to stop a ground loop hum. It's not like that where you have transformer galvanic isolation, because all of this is referenced both at the receiving end and at the transmission end to the ground on the circuit board. You still have to have good ground planes and good grounding practices on your PCB design. So what are some of the parameters that we care about for differential signals? First, let's take a look at what it really is. I mentioned that in the last slide. We have to have, on a PCB, we still have to have a reference ground. So we have two traces routed side by side typically. Sometimes we may have broadside coupling, which we'll talk about later. And we have, at any one instant along the line, if it's well designed, we'll have equal and opposite voltages on the lines and equal and opposite currents at that specific location on the line. And we'll have equal distances from the reference plane to each strip line or microstrip, and we'll have a differential voltage between them. And so we look at V1, that first trace, track 1, in the image there. It's the first trace signal voltage relative to the return plane. So that's our true. Then V2, the second trace signal relative to the return plane. That's our complement. And the V diff, which is the difference between them, is quite simply V1 minus V2. And the common mode voltage, Vcom, is any voltage, the common voltage would be half V1 plus V2. So if they're equal and opposite, the common voltage would be 0, plus some offset, which is any external interference, any induced interference. So we want to route these close together so that they maintain that good common mode coupling, so that external interference affects them both approximately equally as possible. So VDIF is the differential signal, VCOM signal of a general. I needed to change that. That was translated from another language and I forgot to change it. So forgive me, but that's common mode voltage. Okay, so the voltage at any one instant, therefore, on the track 1 would be the common mode voltage plus half the differential voltage. And similarly on track 2, the voltage at that same location in distance along the trace would be the common mode voltage minus half the differential voltage. And I've added some images on the right there, which I used a really cool free open source calculator called ATLC2 that generated these images, if you want to download that and have a look at it. And it gives you a visualization of a static field on transmission line. So at the top, you can see I've created a board layer stack up as a bitmap where the light green color is ground planes, and the red is the true, the blue is the complement, and those are equidistant from top and bottom ground planes. And so this is a not broadside coupled, this is a edge coupled strip line differential pair, and the intensity of the electric field in differential mode is that image in the center to the right. And so you can see there's more coupling edge to edge, but if we drive each of those lines with a common mode signal, that is, we drive them with the same voltage, it couples more above and beneath to the planes, and edge to edge there's zero coupling because they're both at the same voltage potential. So signals that are common mode will couple into the plane. Signals that are differential mode will couple into each other plus to the plane. The reference plane is always there and always important. Okay, moving on. So how do we design differential pairs? What are the different types of differential pairs we might have in a PCB? We have coplanar differential pairs. So that's where you have maybe even a single-sided board with only copper on one side. And I've seen boards done this way for USB and for audio, for analog differential, and for other types of boards where you want some noise immunity because the board may be quite large and you're going over a long distance. And we can still have ground coupling as long as we have a surrounding ground plane around that differential pair on the same layer. So that's a coplanar waveguide style differential pair. It's pretty unusual, but you can do it. Then there's a microstrip differential pair. This is probably the most frequently encountered and ones you may have used. This is where we have microstrip lines that are edge coupled as a differential pair and routed together. They're coupled to a return path ground plane immediately under that layer. So they're on the surface of the board. The embedded microstrip is where you have additional dielectric material above the diff pair. This is pretty frequent in rigid flex designs where you have a differential pair on a flex circuit and you have flex cover lay over the microstrip, and that creates an embedded microstrip. Or perhaps you have exceptionally thick, maybe it's just a microstrip on a regular PCB, but you have an exceptionally thick solder mask, and that can form an embedded microstrip as well. Then strip line is pretty common as well, where you have a symmetric strip line is where, like I showed you in the previous slide, you have edge-coupled differential pair with planes above and beneath. Asymmetric strip line is probably technically the most frequently encountered type of strip line because of the way board lamination is done. The traces that form the differential pair are almost always offset a little bit. And so that's where one ground plane is more closely coupled than the other. And then broadside coupling is where we run differential pairs on we have the true and the complement on different layers, one over the other. And this was how differential pairs had been done before CAD tools had the capability of routing two traces together at once. You know, back sort of 15, 20 years ago, before differential pair routing was possible, a lot of people did their diff pairs for Ethernet, for example, on a circuit board using broadside coupling, because you could route the true on one layer and then make a copy of that and paste it onto the very next layer down in the layer stack. And that's how you would do the complement. Okay, let's talk about impedance. How do we work out the impedance of a differential pair? Because this is important if you want good signal integrity. Firstly, the differential impedance of each line in a pair. This is a kind of rule of thumb way of doing it. Typically, people think of the differential impedance as, you know, based on the voltage. So we'd say the differential impedance is the two individual impedances. And for a lot of designs, this is an acceptable approach. You could treat it that way. You could say the differential impedance is 2 times the single-ended. You know, even Lee Ritchie to this day will tell you that, because the reality is, if you wanted to, on many designs, not on all of them, but in many, you could route the two traces separately on the board, and as long as you have good ground plane coupling, and as long as you have them exactly the same length, most designs will still work. However, we still route them together because A, the tool allows us to do it easily, and B, we still want to make use of some of that common mode noise immunity as much as possible. And so therefore, differential and common mode impedances do play a part in signal integrity. So, so the actual total differential impedance is not exactly 2 times Z, it's 2 times Z plus an adjustment factor based on the coupling between each of the legs in the pair. And that's that formula shown beneath. This is a much more accurate way. And of course, this formula was put together by one of my colleagues in Europe. So I'll just point out here for my audience here in North America that the comma is a decimal point in Europe. So that's 0.48 times the exponent raised to the power minus 0.96 times the space between the true and complement over the height above the plane. Okay, and so we can get more accurate than that using a static field solver, which we'll talk about in a little bit. But the static field solver uses techniques like breaking up and measuring capacitance, like ATLC that generated those images before does it the same way. And there's other algorithms used as well, of course, it could be used for that, like FDTD and so on. So here we have, we talk to the design requirements for a differential pair. So it should have a homogeneous cross-section along the entire length as much as possible. Both lines must be structurally completely identical. In other words, you want to make sure that single-ended impedance of each line is identical. And they have the same etch factors, the same tolerances, the same thicknesses, etc. The time delay of the lines must be matched. So the signal rising and falling edges are synchronized. Otherwise, at your receive end with the comparator, you're going to not measure bits correctly or sample. You're not going to sample the correct data if the true and the complement arrive out of alignment, skewed. And so this, again, this is the reason we route differential pairs together on a board as a differential pair, is to guarantee that we have them as closely as possible to the same length. Okay, to ensure maximum common mode interference immunity, the lines must be closely coupled, which we talked about. That common mode coupling helps with noise immunity, common mode noise rejection. Okay, the return path for a differential pair is just as important as for single-ended lines. So single-ended impedance anomalies will still cause reflections and problem and cause skew in your signal timing, because it's not just the true or the complement trace that gives rise to the amount of time it takes a signal to get down there. It's also the plane return path that has an effect on signal distortion and how long it takes the edge to travel down the board. So let's talk now about what you've all really come here for, which is to see how does Altium Designer handle differential pairs. Well, firstly, every good PCB design starts with a good schematic. And so the first thing you want to know, of course, you can create diff pairs directly in the PCB editor. But good designs will define as much of this and show visual cues in the schematic as well. So if you're working as a team, maybe you're a specialist PCB designer working with an electrical engineer, or vice versa, maybe you're an electrical engineer and you want to tell your PCB designer, hey, this is a differential pair and it will be routed as a diff pair. This is how you define it in schematic. You name the nets the same, but suffixed with an underscore P for the true and an underscore N for the complement. And then you assign or place on that net a differential pair directive. And you can do that also to a group of nets all at once, just by naming them appropriately and then using what's called a blanket, which if we have time, I'll show you that trick a bit later on in the schematic editor. Okay, so then in the PCB side, you can also manually add diff pairs. And there's a really neat little tool for automating this process based on net naming conventions. So you can say, in the PCB editor, look for all the nets. You can either manually add it and you can specify which is the positive and which is the negative, as shown here in this slide. Or you can say, find all the nets which have the same name but differ in some specific way. So maybe you have a board where you've already labeled all the nets with an underscore T and an underscore C for true and complement. Well, you can do that in the PCB panel in Altium Designer, and it will detect all the nets which are the same as the true and the complement, except for that specific difference between them, and it'll generate differential pairs from those for you. Also, how do we get the differential pair impedance? We do that in our layer stack, because of course the layer stack has the most profound effect on our impedance, given the different dielectric thicknesses and dielectric constants and loss factors of those materials. So this is where we get into the really neat fact that we've partnered up with Symbian software that has a very powerful and trusted solver, and their static field solver is built into Altium Designer's Layer Stack Manager. And so this will allow you to go to the impedance tab and create impedance profiles. And those impedance profiles can be either single-ended or differential. And for our purposes today, we're going to create one of those and see how that works. And you can specify your target impedance, and then it will create differential pair impedance profiles that give you the trace widths and gaps for getting that target differential mode impedance to within a very tight tolerance. And you can see the default target tolerance of the calculator is 10%, but it usually calculates the widths and trace gaps to obtain the impedance to within several fractions of 1% or even less. So it's pretty accurate, and it'll give you good results, and we can leverage that in our interactive routing once we've set up those profiles. These are the profiles which are supported by the Layer Stack Manager. So for strip line and microstrip differential transmission lines, we have the embedded microstrip, and you can see we have on the left pane there, you can see it will support different layer stack up orders with cores and prepregs, and that has an effect on the trapezoidal shape or cross section of your traces after etching, and after lamination they go in a certain direction, as you know. So when the very top left example is a differential microstrip where the layer between the microstrip pair and the plane, the reference plane, is a core. And so the trapezoids point up away from the core and into the prepreg, which is laminated over it. The next one, the very next one over to the right of that, the center top of that left-hand group is where the prepreg is between the differential pair and the plane. And the solver can cope with all of these different scenarios. And even, you see at the very bottom of that one, we've got the microstrip differential pair with solder mask over it. And you can specify what your solder mask thickness is in the impedance profile, and it will accurately calculate for you what the differential impedance is in that profile. So there's microstrip and strip line diff pairs supported, and also coplanar, and those include with or without planes. So if you're doing even a simple 2 or 4 layer board where you have a plane layer but it's very distant from the diff pair, it will still take that into consideration and allow you to flood return path planes around your differential pair and calculate it as a coplanar or coplanar with ground differential transmission line. And this is what it looks like. And if you select a specific layer in your layer stack up, it shows you, it highlights the surrounding layers where you can enable or disable those surrounding layers as reference plane layers if you know that you're going to have a contiguous flooded plane above and beneath the diff pair on those layers. If, for example, you have a diff pair on, say, the second layer, like the one we're looking at here, but you know that only the bottom layer, the layer directly underneath it, is a reference plane, but the top layer is not, you can uncheck the box on the top layer and it will recalculate the widths necessary to maintain impedance, assuming that it is then an embedded microstrip differential pair, which is what it would be at that point. And so the system can cater for all of those different scenarios. Once you've set up your differential pair profiles in the Layer Stack Manager, you can leverage them in design rules. So you can go to your width and differential pairs routing rules and specify use an impedance profile. And even if you disable certain layers within the layer stack for that impedance profile, those will also be left out of this rule, and that can also help to prevent you accidentally routing the differential pair on a layer that you shouldn't be routing it on. So that's quite a useful little feature there. But note that it automatically gives you the correct minimum trace widths and gaps and preferred trace widths and gaps all through the layer stack based on that impedance profile and the field solver's calculation. So it's very accurate. Now, before we jump into questions, let me just really quickly show you what this looks like in Altium Designer. So I'm going to switch over here to Altium Designer. Let me just make sure I'm still sharing the right screen? Yes, I am. Okay, so now we're looking at schematic, and this is a multi-board project. This is a little Wi-Fi dongle that goes into a mini PCIe connector. Now we're not using the PCIe bus, so most of those connections are left floating. We are, on mini PCIe, you also have a USB, so that's what's actually being used here. And as I pointed out before, we name them the same, but with _P and _N, and we add these diff pair directives, which come from the active bar just up here. If I right click on that, there's a differential pair directive. Another way of doing that, and I'll show you very quickly how to do this. If you have more than one net and they're all going to be differential pairs, let's say you have a whole bus of diff pairs, maybe an LVDS bus with 8 differential pairs or something like that, and you want to, you've named them all with the _Ns and Ps, but you want to add that directive to all of them. You can do that using what's called a blanket, and this is where you place this blanket around those. Let me finish that. And what I want to do is place it so that these net labels are wholly contained within the blanket or touching it on its edge. And then I can add the differential pair directive, and anything touching or within that blanket that has the appropriate net naming will become a differential pair. So that's a quick way of doing it for a large group of objects. Of course, I didn't need to do it here just for this simple USB connection. Now let's see what this looks like in the PCB editor. Again, this is a pretty simple design, but there is the diff pair. It's already pre-done. So what I want to do is actually show you what this might look like. I'm going to go and show off all the polygons, and I want to select, I'm just hitting tab to select that routing, and I'm going to delete that. And let's go into the layer stack manager from the tools menu here. Okay, so this is my board layer stack. It's a simple 4-layer board, and it meets the spec for mini PCIe with a 35mm core and 2 8.2mm prepregs. It's 1 ounce copper on all layers, and we can see each layer already has our constructions defined and materials selected. And there's some questions coming in. I'll get to the questions soon. And so we go in Layer Stack Manager, we go to the Impedance Profile tab down here. And I've already set these up, but let me delete them and start again just to show you what it would normally look like this when you start. Okay, so you go to Impedance, it sets up this blank area, and you can either click the plus sign or click Add Impedance Profile, and it by default gives you a 50 ohm single-ended line. Well, I don't want that. I want a differential pair. I'm going to go differential, and I can specify it's differential or differential coplanar. This is just basic differential, and this is going to be USB 83, because USB 2.0 uses an 83 ohm differential pair, and the target impedance is not 50, it's 83 ohm. And let's say I want that to be maintained to within 5%. Now, if I'm doing a very, very long signal line, just something I'll point out here, I won't actually use this, but you can choose a copper roughness model, and this is used, there's different models supported by the solver, and this is used for determining loss factors in dB per inch or dB per meter. If you're in metric mode, it'll support either. And so if you want to do that, it'll give you that information. Over here, it's now created that differential pair profile for me throughout all the layers of this board. Now, in this case, I'm saying I'm going to route this entirely on the top or bottom layer. So my bottom layer differential pairs are referenced only to the next layer down as a microstrip, and you can see the image over here is showing me my layer 1, 2, 3, 4, layer 3 plain, and layer 4, which is bottom. has solder mask. So we can see that there, and I can specify what's my mask thickness. Do I want to use mask or not? If you're planning on opening the solder mask over the diff pair and just having bare plated copper, you can do that if you want and just leave out the solder mask by unchecking this box here. And then the solver knows you're going to leave the copper bare. I'm going to include the solder mask, and I'm going to specify what the mask thickness is over the traces and over the board surface on its own. You need to specify that in two places because mask is spray painted onto the board and then hardened with UV light. So it's typically thinner over the traces than it is over the bare board surface. So if you want to specify the covering thickness, you can do that. You'll need to talk to your fabricator and get them to give you a sample or cross-section data about their process to know exactly what those thicknesses are. You can also specify your preferred trace gap. And I'm choosing 5 mil because I think that's a good round number. 5 mil track and space, 5 mil gap is any low-cost board fab can do that these days, so I'll stick to 5 mil. And you can see I can also add in the etch factor, and an etch factor of 1. Let's make some room here for a second by minimizing these sections so we can see. Where are we? It's hard to see on the screen sharing on a webinar, but there's a tiny little help question mark next to etch. And if I hover over that, it says, what's the etch factor? It's half the width. It's half times the base width, half times the base width minus the trapezoid width over the thickness. And that's from the standard, industry accepted etch factor, which you would know if you're a CID, you would have studied that in the CID training class. They talk about etch factor, and basically it's if you have a 1 mil thick trace, it's going to be half of a mil per side. So per 1 mil of thickness of trace is generally what it works out to be. So that's what an etch factor of 1 does, and that gives me over here solved trace width needed of 11.169 mil with a gap of 5 mil, and this gives me a differential impedance of 83 ohms exactly, and a delay of, let's see, it's going to be 156.626 picoseconds per inch for that transmission line. Now, of course, I could make adjustments. Let's say I don't like that to be so thick as 11 mils. Let's say I want to bring that down to 10 and see how is that going to affect my target impedance. This now tells me a warning mark saying that the trace impedance now exceeds the specified tolerance. So a 10 mil down to a 10 mil trace is going to be 96 ohms, right? So I could start changing things, like I could start playing around with. So it works both ways. The solver works both ways. If you want 10 mil track in space, that'll give you over a 100 ohm impedance. If I go down to 4 mil space, it gets it down to 91, but it's still too high of a differential impedance. So let's bump this back up to 11 mils. Now it's 92. Let's go to 12. Now it's 88, and I'm within 10% now of my target, right? Or I could come back here. And click this FX button to have it reset to give me the trace widths and spacing, which is up closer to 14 mils, to get my target 83 ohms. So now that I've set that up, if I save my layer stack and go back to the PCB, I can go to design rules. and go to my differential pairs routing and go to use impedance profile. If I wanted 83 ohms, this is now going to give me these fairly wide traces on the microstrip sides of the board. How would I reduce that if I wanted to? What I'd have to do is modify the layer stack to have a much thinner dielectric between the signal layer and the reference plane layer. So I could reduce this thickness from 8.2 down to say 4.1, and that would give me thinner traces for my diff pair, because that reduces the impedance. But now that in design rules I've referenced that impedance profile, it's given me the correct widths and everything for the different layers. And now I can route the pair using the differential pairs routing. And I can route it just like any other single-ended trace. Now here I'm running into some trouble where I need to neck down to get in. Oh, I can just do it. I just made it through. And let's see. I'll hit spacebar to control this a bit better. And that's basically it. Now, of course, the system, the routing will, if I'm just doing basic trace adjustments, it will keep the pair together, even if I grab that inner segment. And if I want to gloss this, I can select those segments, hit tab to select the whole connection, and Control-Alt-G will gloss this and improve as much as possible. It will shorten and make the routes much more direct. And if you do that after having enabled gloss mode with curves, it'll also put curves in. So that's it. I mean, that's all we've really got time for right now, but I will open it up for questions. So let me go to the Q&A. There's a couple of questions in here. So Puria, I hope I said your name correctly. Forgive me if I didn't. You're asking, I have a problem for adding _P and _N label number for several different signals automatically. For example, I want P1 _N and P1 _P, P2 and so on, how to set it automatically. I think what you're saying is you have a bus of differential pairs which are suffixed with different numbers for each bit, and you want to add the _N and _P. At this stage, there's no automatic way to do that. However, how I would personally do it is I would route them all on the schematic first using the number suffix, and then I would use the list panel, which you can open with Shift F12 and find all the net labels that have that same bus name. Let's say it's P, the P bus. And then sort them according to their location. And then I'd go through, it's just like a spreadsheet view of the net names at that point, and modify each one in the list. And that's a much faster way of doing them all, using net labels. So that's just how I would probably attack that problem. And then you have all those names and you can easily add the _P and _N to the right ones. Lyndon, you had a question saying, I often use 1/2 ounce copper on the top layer, but it gets plated up to 1.5 ounce. How do I get this accurately reflected in the stack up? It wants to jump between 1 ounce and 2 ounce. You can actually specify the thickness. If we go to the layer stack manager, here under weight, that's the actual copper weight, but you need to adjust the thickness. And you can type in this field. You don't have to pick from this drop down. The drop down's there for convenience, but you can type 1.5. The other thing you can do is add a material to the material library. Let's say this is 1.5. So this is going to be, let's see, half 1.4 is 0.7. So this is going to be 2.15, say, 2.15. So you can type in the thickness directly. It will then jump to the nearest one on the display, but the thickness is what's actually being used for the calculation. So if you have 1.5 ounce copper on top, and note, it doesn't, let's go here and recalculate this. It doesn't make a whole lot of difference to the trace thickness, the trace width, sorry. It's a lot thicker, but the impedance is almost exactly the same. And the system knows that because it's the way that the signal is coupled to the plane. It's on one side of the trace, and at high speeds, most of the current is traveling only in the thin layer of the surface because of skin effect and proximity effect. And so, so it doesn't really profoundly change the dimensions of your trace in terms of width and gap. So those were only 2 questions that came in. Let me see. Let's see. There was a couple of questions came in through chat, I believe. So we have from Eric. Is the reason that the forward voltage drop of the diode being 0.5 instead of about 0.1 to 0.2 because of lower current between the Schottky, or as opposed to larger current? No, not being the guy that designs the chip, I can't answer that with a great degree of confidence. I'd say they're usually Schottky diodes. Schottky diodes aren't always a 0.1 or 0.3 volt drop. It may depend on the dimensions within the silicon. But I would also say it may not always be a Schottky diode. It may be a silicon diode that's being used. It really depends on the designer of the chip and the I/O. Now a question just came in from Matthew. I hope I also said your name right. It looks like a French spelling. Can you manage different DK/DF values when signal frequency changes? At this stage, I believe those are static in our field solver and our material library, because the only fields you enter when going into the layer stack material library are static, a single DK and a single DF, but you specify at what frequency. I'm hoping that we release an update which allows a curve to be put in. But the truth is, I've looked into this, and between 1 gigahertz and 15 gigahertz, most materials don't change very significantly in DK and DF over that frequency range if they're good quality materials. Some specific materials for RF and microwave design do have more of a variance to where there's an optimum region in frequency, and you want to be super accurate to create exactly the right shape on the board for an RF filter or something like that without shifting your center frequency or bandwidth too much, then yes, you really need to care about, does DK and DF change significantly over frequency? So I'm hoping that we add that in a future release, but at the moment it's just a single value. Another anonymous question, will there be a recording? Yes, I have recorded this entire thing and it is still recording right now. So when we finish, if you signed up to attend the webinar, you will be sent a link to the recording afterwards once the recording is available. So if you missed something, please do go back and watch. Anything else? I think that's it. So I'll just say, please speak now or forever hold your peace. If you have any other questions or comments or feedback for me on how to make this an even better webinar, we would definitely appreciate it. And please let us know. So, okay, here's another question just came in from Boris. Will there be a transcript with the recording? Oh, well, that's a great idea. Normally we don't do that, but if I can find a way to do it so that we get the text, I think I will do that, because then when we put it up on our website, it's also good for SEO. So thanks for the idea. I'll see if we can. Can't promise it, but hopefully. Jeff asked, can you attach your ATLC calculator bitmap file? Yeah, sure, I can provide that. No problem. Again, I don't know where I would add it, but I'll find a way to get it to you. It's pretty easy to reproduce though. Here's the thing about trace dimensions and impedance is it's all relative. So if you're using a field solver, they're unitless. So everything is normalized basically down to pixels in an image. And that's how ATLC works. So you don't even have to say this trace is 11.596 mils wide. You can make it that, but if it's let's say if it's 10 mils wide and the gap is 5 mils and the other trace is 10 mils, and you have a dielectric above the plane that's 8 mils, well, you can have 10 pixels, 5 pixels, 10 pixels, and 8 pixels. Because the field solvers, they don't care about mils, they care about relative distances. And so that's the beauty of these kinds of calculations, is that they're all about relative distances. And you can scale up or down. You can make a 100 ohm transmission line on a PCB that has 5 mil gap, and then scale it up and use the same dimension transmission, same relative dimension transmission line for a high powered RF amplifier, but with a thicker substrate, and the traces will be much wider. And you want that because you're going to be carrying some pretty heavy currents. And so, yeah. Okay, well, one more time, one more last call for questions before I close it out. Can the impedance profile be handled by active route? Yes, active route will follow your design rules, and the design rules are determined by the impedance profile, so yes. As long as you set up your differential and single-ended impedance-based width and clearance rules, you can use the impedance profiles in width and differential pair rules. So if you call out your impedance profile, active route, and the gloss engine, and all those things, they will use the impedance profile that you've set up in the layer stack manager. Okay, well, I hope that's really good for everyone. I will let you get back to your daily routine now, and I really appreciate you attending. Again, please feel free to email us, watch the recording, leave comments. Once the recording's available, I believe the page where the recording is hosted has the feature underneath where you can leave comments as well. So feel free to do that if you have any other questions. And I really appreciate your time. And thank you again for joining me for this differential pairs webinar. And I hope that you'll stay safe, enjoy family time, and hopefully soon we'll all be able to go back to the office and enjoy each other's company again. So thank you and see you later.